Hi, everyone. In today's lesson, we're going to talk more about the natural logarithm and the number e. So let's get started. So before we begin, just want to review the inverse of a function. So the inverse of a function results from a transformation that just swaps the x and y values. So what you learned in your grade 11 course is that it looks like a reflection in the line y equals x. So we're going to quickly look at more detail the properties of the exponential function 2 to the power of x and its inverse, and then we'll extend these ideas to the function e to the power of x and what its inverse is. All right, so to start off, we'll just do a quick sketch of what the sketch of 2 to the power of x and its inverse is. We'll derive the inverse too. So this will be a review for you guys. So 2 to the power of x has a y-intercept of 0, 1. It's just powers of 2. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. 2 to the power of 2 to the power of -1 is 1/2, and then a quarter. And then it's a bit too impractical to sketch. But there's a sketch of 2 to the power of x. And a sketch of the inverse. So if we make a dashed line, so that represents y equals x. We take those points and just kind of flop their values. So 0, 1 goes to 1, 0. 1, 2 goes to 2, 1. 2, 4 goes to 4, 2. We get 8, 3. We can even go -1. 1/2 goes to 1/2 -1. And then a quarter -2. We get the graph of the inverse. Oh, that was terrible. That's okay. Right shape. Missed a few points there. No big deal. So let's derive the inverse of this function. So the way we did that in our grade 11 course, we flip-flopped the x and the y. So x equals 2 to the power of y. And then yesterday, last lesson, we reviewed our logarithm rules. And we had one rule that actually allows us to get a variable or something out of an exponent. So if I take the log base 2 of each side, base 2 of 2 to the power of y, using our log rules, I can bring down the y. So y times log 2 base 2. And log base 2 is just 1, because 2 to what exponent gives you 2? Well, it's just 1. And we actually get the inverse function y equals log 2 of x. So nothing really crazy new here, just a bit of review for you guys. Let's review some properties of these functions, and we'll see that a lot of these properties are just kind of like reflections of each other, or having to do with the inverse. So the domain of 2 to the power of x, we know that you can plug in any value you want into 2 to the power of x, and you'll get a meaningful result. But the range, you only get certain y values. You get real numbers that are greater than 0. And so I might flip back and forth between these guys here. So we can see that the graph 2 to the power of x goes on forever and ever. Like, it'll have a value for like at any x value left and right, but it's only above the y-axis. But you can see with log base 2 of x, you can only plug in x values that are positive, not 0 or negative. And it's the y values. You can get any y value you'd like from log base 2 of x. Goes forever up, forever down. So for the inverse, which we talked about, was y equals log base 2 of x. The domain is x is any real number greater than 0. The range of this function is y can be any real number. The graph of 2 to the power of x is increasing. The graph of log 2x is also increasing as we go to the right. The y-intercept of 2 to the power of x is 0, 1. Now note that this corresponds to an x-intercept for log base 2 of x because they're inverses. You flip the x and y value. There is no value. There's no x value that makes the y value 0 for the exponential function y equals 2 to the power of x. That means, conversely, there is no y value that gives an x value of 0. And you can see from the graph that log base 2 of x has its x-intercept at 1, 0 and has no y-intercept. And of course, all these things are true for any base. We're just using 2. The exponential function has a horizontal asymptote at y equals 0. This corresponds to a vertical asymptote at x equals 0. Again, switching x and y. And exponential function has no local max or min, no inflection points. Same thing with the log base 2 of x. All these properties for 2 to the power of x are going to hold for any base b. I know these aren't equal. I'm just trying to illustrate that these properties we have here, it's true no matter what b is. And these properties we have on the left are also true no matter what b is as well. I should say for b being greater than 1. Which is kind of what we're interested in because we talked about our last lesson, this number e, which was that special base where the derivative and the function were the same. And we saw it was about 2.178. So the properties we're talking about here with 2 to the power of x hold with e to the power of x as well. So we did all that work with log base 2, and we talked about that special number e, the natural number. So what would the log base e look like? Well, this is what we're talking about now. We call this the natural logarithm when the base is e. So we're talking log base e of x. We actually give this a special name. This e has a lot of special properties. We've seen a few, but one of them was that the derivative of e to the power of x is actually itself. The natural logarithm, log base e, is used so much, we actually give it its special name. It is the ln of x. Ln x. Just like, log base 10, you just don't write the 10, you just write log. Well, ln implies log base e, so that's important. So the function y equals e to the power of x, in the natural logarithm, y equals ln x, have all the exact same relationships that 2 to the power of x and log base 2 of x have. So that was kind of the main goal of this setup, is to introduce the natural logarithm, ln x. It's just the inverse of e to the power of x, e being that special number around 2.718. Let's do some quick examples. To be honest, the goal of these examples here is actually just to kind of find these features on your calculator. So most of you guys will have a button like this, e to the power of x. That allows you to do powers of e. It allows you to actually type in e as well. If you do e to the power of 1, you can see what e is to a bunch of decimal places. We'll also be using the ln button. So many of you guys probably thought that was saying in, because it might just look like a capital I like this on your calculator. No, it's actually the ln. It's the natural logarithm. So I'll do these two. And yeah, again, these are just getting us used to our calculator. For me, I'm not sure you can see that. When I press my e to the power of x button, which is right there above my ln button. Yep. When I press second function that, I get an opportunity to plug e to some power in. So I'm doing e cubed. You should do it too. Again, we're just making sure that we all know where this feature is on our calculators. It's about 20.086 e to the minus a half. So you can just use your calculator to do that. Punch in e to the negative 0.5. You get about 0.607 to 3 decimal places. Of course, that's equivalent to 1 divided by the root of e. And if you did that, you get the exact same thing. Try out your ln button. So the ln of 10, about 2 decimal places, the ln of 10 is equal to about 2.30. So if you want to just do a quick check, what that means is e to the power of 2.30 is going to give you approximately 10. So you can try that out if you'd like. Try ln of negative 0.5. Sorry, negative 5. Hopefully you're like me and you got an error. I'll just put equals error, which actually makes sense because if we go back to what we talked about earlier, the domain of a logarithmic function is x has to be greater than 0. So it makes sense we got an error message that because there's no y values for x less than 0 on any logarithmic function. So that's okay that we got that. And lastly, ln of e. Now you actually shouldn't even need a calculator for this because remember, I'm going to write this out for this one. Ln just means log e base e. So e to what power gives you e? Well, that's just 1. But if you want to verify it on your calculator, yeah, ln of e is equal to 1. So hopefully you found those out on your calculator. You got some experience using them because we're going to be using those today to solve some problems. Some useful properties that you guys know from your earlier work with logs. I'm just going to write these properties in terms of e. So the first one I want to talk about is the following. Because these are inverses of each other, like for example, you guys know, if you do, within reason, the root of x squared gives you x, right? When you do the inverse of an inverse. The same thing is true with exponentials. So if I do e to the power of ln x, this is just equal to x. So why is this true? So you can write this down or not if you'd like. But remember, ln is like log base e. So in the exponent there, the result of log base e of x gives you the exponent where you do e to that exponent, you get x. Well, if you do e to that exponent, you should get x. So that is some property that takes some students a while to get their minds wrapped around. But it's kind of related to this. The inverse of an inverse is just the original, like the root of x squared is equal to x. So that's going to come in useful. A second property that will come in useful is that the converse is true. The ln of e to the x is just equal to x. And again, you can use your logarithm properties for that because you can bring down the x as an exponent, and the ln of e we know is equal to 1, right? So we get x with that. What these properties allow us to do is allows us to take any function with any base and rewrite it in terms of e, or take a function that's in terms of e and rewrite it. So we'll see that in this example here. So here we have a population of bacteria. It's increasing as a function of time, and you have the equation there. 200 times e to the power of 0.094 t, where p is the population after t days. Let's do part A. We might do part A, B, and C on this slide here. So part A, the initial population, well, we're looking for p at 0 here. So we have 200 times e to the power of 0.094 times 0. That's 200 times e to the power of 0. Of course, that's just 1. So we get 200 times 1, 200 bacteria. Why don't you guys try that for part B? Part B, you're just evaluating this population function after 3 days. So 200 times e to the power of 0.094 times 3. And I showed you guys where your e button is, so we should be able to do that. Some of you guys will be able to do this all in one step. Some of you guys, maybe like me, just want to do this in a couple steps. So it's 0.094 times 3. That's 0.282. And I'll do this all in one step. So I'll do e to that result, 0.282, and then multiply that by 200. So I get about, to the nearest whole bacteria, I got about 265 bacteria in 3 days. Let's do part C on my next slide. Just at the same problem here. So how long will the culture take to double its population? So doubling the population from 200 to 400, then we're setting P of T to 400, and we're going to solve this equation for T. So this might be one of our first examples of actually solving an exponential equation. I think we might have done some in a warm-up yesterday. But let's isolate the exponential stuff. So divide both sides by 200. You get 2 equals e to the power of 0.094 t. Our goal is to get that t in the exponent. We want to isolate it. Our way to do that is we're going to take the ln of each side, because our base is e there. So we want the log base e, but we know that is equivalent to, we call that ln. And from our properties we just talked about, remember those are inverses of each other. That is just equal to ln base e, ln of e to the power of 0.094 t is actually just 0.094 t. And we can solve this. T is equal to ln 2, whatever that is, divided by 0.094. And so you guys can crank that out. You guys now know where your ln button is. Ln 2 divided by 0.094. I got about 7.4 days. And you could, if you wanted to, you could check that answer and plug in 7.4 into that original function, see if you get roughly 400. So that's an example of how we can solve an exponential equation where the base is e using the natural logarithm. So you guys now have that in your toolbox. Now, something we've talked about and what you for sure talked about in earlier courses is that there's actually many ways to write exponential functions. So for example, here's a simple one, 4 to the power of x. Well, I could write that as a base of 2. 4 is equal to 2 squared. And using power rules, I could write that as 2 to the power of 2x. These two functions are the same function. One's base 2, one's base 4. So in terms of transformations, the graph of 2 to the power of 2x is actually just a horizontal compression by a factor of 2 of the function y equals 4 to the power of x. You might have done an exercise or two like that in your grade 11 course, but the reality is I could take the function y equals 4 to the x, and I could write that as an exponential function with a base of 3 or 10 or e. I could do a lot of things. So actually, that's what we're going to do here. We're going to rewrite this function as an exponential function having a base of 2, which would be helpful if you were looking for like what the doubling time was, for example. So let's do that now. How can we do that? I'm going to rewrite my function here. E to the power of 0.094 t. All right, so we would need to write e as a power of 2. So how do we do that? Well, I'm just going to shift things over a little bit. So we have our 200. All right, so here we go. I'm going to write this. I'm going to write e as 2 to the power of log base 2 e. So remember, using that property we discussed earlier. So log base 2 is saying 2 to what exponent gives me e. Well, that 2 to that exponent that the log gives you is equal to e. So this inverse of this property actually gives you e back again. So that does take a little while to kind of get used to. But because 2 to the power of and log base 2 are inverses, we actually get back e. And then we have 0.094t. So we get 200. So using exponent rules, we get our base of 2. And in the exponent, we have log base 2 of e times 0.094t. Well, fortunately, you guys know how to evaluate logs with different bases. That's equal to log e over log 2. I'm going to just be stubborn and squeeze everything in here. Log e over log 2 times 0.094t. And then we can go to our final answer. So we have 200 base of 2 log e, excuse me. And when you're using that, you can just do e to the power of 1. That gives you e back, divided by log 2 times 0.094. So in the exponent, we get 0. I'm just going to keep a lot of accuracy here. 0.136 t. So we've rewritten that exponential function in terms of a base of e as a base 2. And the key was this step right here, writing e as 2 to the power of log base 2 of e. One last thing. You may recall from back when you learned about exponential functions that you can write exponential functions in terms of a doubling time. So our function here has an initial value of 200. And we found earlier that it doubles every 7.4 days. So you might have written that as, in grade 11, 2 to the power of t divided by your doubling time. So if you actually compare what we just did with this function with the doubling time, you can actually see they're the same. If you do 1 divided by 7.4, you're going to get pretty close to what we got earlier. I got 1.135. We have 0.136 here, just with rounding and stuff. But yeah, I thought that's a pretty interesting connection to make. All right, guys. So anything you can do with logs, you can do with lns, the natural logarithm. And then our next day, we're going to see that the natural logarithm ln actually plays a big role in the derivatives of exponential functions. So all the work we did the previous day about connecting the derivative of an exponential function and how they were constant multiples, we're going to see that the natural logarithm actually plays a role in that. For now, got some practice for you guys from the McGraw-Hill-Ryerson text. As usual, I'll post a resource for video solutions as well, and just written solutions. But I hope you guys will reach out if you need anything. Hope you guys have a great day, and we'll see you soon.